Okay. Okay, well, thank you all for the invitation. I'm really excited to be here. And what I want to talk to you about now, I guess, in the first talk is possible shapes of space as a mathematical problem. So let me see. Oh no, does the keyboard not click? Does this click? Does the mouse work? Okay, the mouse works. The keyboard doesn't work. I'll use the mouse. We're good, we're good. Let me just keep the mouse. Oh, no, mouse doesn't work there. Okay, mouse only works here. Interesting. Okay, we're good. We got it. Okay, so the mathematical problem that I'm interested in, honestly, the problem that got me interested in becoming a mathematician is the world around us is three-dimensional. We've known that sense forever, and we've even known the mathematics of that sense forever, or more or less since the beginning of writing mathematics down. These days, we might formalize this, like when we're talking in undergraduate mathematics classes, as, how do I say the world's three-dimensional? I say the world looks like the vector space R3. And that's what we see around us. That's what Euclidean geometry applies to everything we see nearby. But we might ask ourselves, what is the world like far away? And there's two ways we could interpret this question. One is like, what is the large-scale behavior of the world? And the other is just like locally, what does the world look like in other spots? Like, does it always look like it looks around us if I were on a planet somewhere far away or in the distance? And Copernicus had an idea about this, which we now name the principle after him, saying, well, we're not special. We shouldn't think of ourselves as special. We see the world around us as looking approximately like the vector space R3. So how should I imagine, without any other data, what the whole large-scale picture of the world looks like? I shouldn't guess as to its global nature, but I should say locally it probably looks like this everywhere. And whether or not that's true of the real world, it's a very interesting mathematical question to try and say what kinds of spaces satisfy Copernicus's constraint here. So I'm calling these here the Copernican worlds. In math, they're called the three manifolds. So spaces that are locally just like our space here, but we don't know globally at all anything about the space. And so as a mathematician, one interesting question would be, what are these? Can I make a list of them? Can I think of any of them? And of course, people have thought about this for a long time. Actually, in the 1700s, Kant thought about this maybe more in terms of geometry than topology, how we might phrase it today. But one reasonable guess as to the answer to this question is, well, this one's logically necessary. Like, space looks like R3. If it's supposed to look like R3 at every single point, what's the only option? R3. That might be all you could think of. That's probably all I would have thought of if if we didn't have a lot of math before to help us see. And so the problem is really the difficulty of imagining what a 3D world would look like, because I just live in a small local piece of it. So one thing that I really like to do when working on mathematical problems is see if there's a simpler test case that I could study first. And here, luckily, there is a simpler test case. I could say, what if I was an ant? What if I lived in two-dimensional space? And I had Ant Copernicus ask me, what are all of the ant Copernican worlds? I.e., what are all of the two-dimensional manifolds? Things that locally look like the plane, but globally no idea. And again, your Ant Kant might say maybe it's R2. Ant me would probably say, well, R2 for sure works. I could check that. But I don't know it's the only answer. And indeed, as a three-dimensional person, I can see lots of two-dimensional worlds. Namely, any surface is a two-dimensional world. Like this table, the sides of a bicycle, this keyboard. Everything in the world around us locally looks like a little tiny patch of surface, but globally could be very complicated. Which leads to the great math question. Okay, can we do this? Like I have a little bit of insight here. I can see a lot of these worlds. I can do a lot of things because I can use my three-dimensional intuition to understand them. But is there any hope of classifying them? And I tried to draw this picture to make it look intentionally scary if you haven't thought about this problem before. Like that, I don't know, that thing looks scary to me. How am I going to classify that? But more interestingly, surfaces don't always come to us as like, here's a blob sitting in space in front of me. Tell me what surface this thing you can see is. Here's an example. Surfaces sometimes show up in math problems that maybe you weren't thinking about surfaces, or they just show up other places. Here's an example. If you take complex numbers for x, y, and z, you look at solutions to this equation up to complex scaling. This is a surface. It's a two-dimensional surface. And Klein, among other people, asked, what surface is it? We'll answer this later in the talk, but this is an example of like something that might be hard. Like, you can't see the surface right away. We can just show this thing is two-dimensional, but who is it? If I truly can make a classification, I'm going to have to be able to sort this somewhere in my list of two-dimensional worlds. How's that going to work out? Here's another example of a surface. The surface of any object in 3D is a surface. So I'm going to have to be able to put this, or any sculpture, or anything you like, in my list of surfaces somewhere. How am I going to do that? I'm going to need to understand things algebraically. I'm going to need to understand things like this from reality. I'm going to need to sort them all. And so the first thing we need to understand, if I'm going to try and sort everything in the world into these little categories, I'm going to need to tell you what counts as a good job. When have I actually sorted things? When are two things the same? And so I'm a topologist, and so to me, these two things are the same. I'm going to say, yeah, this surface looks a little different than this surface, but the way it looks different is it's just kind of bent or extruded a little bit. Oh yeah, that's right, the animations don't work, sorry. There is a bunch of really fun animations, but they're going to be black. So this was animating that, a path of metrics on space in R3. To motivate this definition, so when we're going to call two surfaces the same is when they're homeomorphic, which means that there's a continuous bijection with a continuous inverse. I can map back and forth between the top and the bottom shape, one-to-one in a continuous way in both directions. Then I will count shapes as the same. And since that's how I count shapes the same, everybody makes fun of me and all of my friends and says that topologists can't tell the difference between a donut and a coffee cup. And a lot of times you hear this said because there's one hole in each of them. And that is true. That presupposes the classification of surfaces we're going to talk about. How would I know that's enough? But I can actually show you why it's the same. Two of my friends, Henry Siegerman and Keenan Crane, made this cute little set of displaying a homeomorphism between the two, actually displaying an isotopy between the two. You can get from the coffee cup to the donut. You can kind of track smoothly going along and confirm if you try to imagine what a point does as it goes all the way around, you'll get a one-to-one continuous map between these two. That's what we mean by the torus or the donut and the coffee cup being the same in the classification that I want to make. So here's a cartoon. This is what we want to do. If I'm trying to solve the two-dimensional case of the three-dimensional thing I'm interested in, I want to take this big collection of surfaces coming at me from all over the place in mathematics, and I want to sort them into boxes. And those boxes are homeomorphism classes. Anytime I can continuously biject two of them, they go in the same box. So that's our game. And the game sounds hard, but luckily we live in the future relative to a lot of really, really, really smart people. And the game's been solved. The game's been solved multiple different ways, but the way I want to talk about today is a geometric solution through the uniformization theorem. So it's a theorem of Felix Klein, Henri Poincare, Paul Koebe in the 1870s, 1880s, finally proved fully in the early 1900s. And okay, there we go. I had the date. I didn't need to guess. There we go. 1883. So here is a statement of what this result says, and then I'll tell you how this helps us. So you can prove that every surface can be built using concepts from different parts of mathematics. Here we use something called group theory. We also use some stuff from complex analysis. And together we claim we can build all of these two-dimensional worlds that I care about. And I can build them from three simple two-dimensional worlds. I can build all of them either starting with the sphere, starting with the plane, or starting with the unit disk, and using these tools from math. And this didn't only inspire a lot of mathematics, but it inspired a lot of great art. So a lot of Escher's work on circle limits and other things. Here's actually an illustration from Escher of the three different cases. Here's a symmetrical tiling of the unit disk. Here's a symmetrical tiling of the plane, and a symmetrical tiling of the sphere. And this sort of symmetrical tilings, this is the group theory part. When I was saying we're using some tools from math to do the classification, this is kind of illustrating those tools. Okay. Imagine in your head a video of a torus on the surface of the 3-sphere turning inside out with a bunch of grids on it. Okay. But I guess you can imagine this anyway. Take a donut. You can draw a grid system on a donut. The donut in R3, those grids aren't all going to be the same size. Some of the ones on the inside are going to be a little smaller. Some of the ones on the outside are going to be a little bigger because the torus is bent in 3-dimensional space. But abstractly, it doesn't have to be bent. Uniformization tells us we can actually make it so that we can study the geometry of the torus. We can study the topology of the torus by studying this pattern in the plane. And then we can come back to more complicated examples like this. How am I supposed to study a weird surface like this? Well, once I know that this surface has to somehow come from the plane or the sphere or the unit disk using a bunch of tools in math, I can try and apply those tools and figure out which one it is. And this surface is called the Klein quartic because Klein applied those tools and figured out which one it is in 1890. It comes from a symmetrical tiling of the unit disk. Instead of having nice little squares like we had for the donut, the surface that goes with that picture is associated to this tiling inside of the disk. This would actually go on forever, but this is showing the piece of it that's relevant to building this particular surface. And once you know this, you've turned that into a geometry problem. I can now carefully try and imagine how to glue this up into some interesting way and see what the surface looks like. And people have done this. It turns out it looks like a tube kind of drawn around the edges of a, whoops, don't want to trip, drawn around the edges of a tetrahedron. In terms of surfaces, we'll see in a second, this is a genus 3 surface. It's a surface that has 3 holes in it. And there's actually a really nice sculpture of it made by Helmut Ferguson. It's at MSRI up in Berkeley. This Klein quartic surface. That's an animation of it. But great, so once we have these tools, the point is we can use this theorem tells us, okay, the classification of surfaces is scary. There's a lot of things that could happen. But it gives us a way to get a handle on it using a bunch of different tools from mathematics. And we can prove in the end that the classification isn't that scary, or the answer isn't that scary after all. It turns out every orientable compact surface fits into this list. You're either a ball, a donut, a double donut, a triple donut, a quadruple donut, and so on. And so when we talk about these in math, we classify them by genus. Genus means the number of donut holes in our surface. So if later I said a genus 5,000 surface, I would mean a donut with 5,000 donut holes in it. And this is great. This is a pretty simple list. Originally, surfaces looked like they're very complicated, but it turns out we can determine everything just by one number. Abstractly, how many holes does it have? So we were able to use some math about tilings to figure out the answer to Klein's equation-based surface. And now we can use this answer to figure out the topology of a surface like this. Seems scary at first, but once I know that surfaces are classified by their number of holes, I could just go up to this sculpture and count the number of spots that I could put my arm through. I didn't actually count it on this picture. I did look for a 3D model of a sculpture that I could rotate around and count the genus for you, but I didn't. But you could imagine doing it. And so this gives us a practical way to do it for surfaces in the real world. We can understand which of these boxes, which homeomorphism class it falls into, without actually having to do any of the math once we know the answer, the classification by genus. Okay, so that case is a beautiful piece of mathematics, the classification of two-dimensional manifolds. But remember, what I want to tell you about today is well, not the real world case. Like, I'm not talking about general relativity and Lorentzian 4 manifolds, but I want to talk about the more real to us version of this case. Namely, remember, what are the spaces that locally look like R3 everywhere? Not surfaces, but three-dimensional versions called 3 manifolds. And well, remember, you might think, before you've seen the full solution to the two-dimensional case in the 1800s, that maybe there's not many. Maybe, like, if it looks like R3 everywhere, it is R3. But But that's not the case. As we can probably imagine from surfaces, you can make something pretty scary. But what's cool to me is people already knew this, or at least person already knew this. The first case that I've seen where it really seems like someone knew about a space called the three-dimensional sphere is Dante in the Divine Comedy. So Dante talks about the structure of the world. And the way he describes the world is built out of layers, like an onion. There's earth, and below earth, there's a bunch of these levels of hell. And above earth, there's a bunch of these levels of heaven. But as below is above. So as when you go to the center of the earth, you eventually reach a point. The spheres get smaller and smaller and smaller. So do the spheres of heaven. As you get higher and higher, they get more selective. And at the top, you hit, I forget what he calls it, but like perfection. You hit the very top level. It isn't some giant celestial sphere. As you go off of the earth, they get smaller and smaller, and they converge to a perfect point above and below, with the earth in the middle. And so if you try and draw this picture, well, I can't draw this picture because there's not enough space around me to draw it, but I can do the dimension jump thing. I can draw the two-dimensional picture. What would it look like to have something that looks like a circle that gets smaller as it goes up and it goes down? Well, that looks like slicing the sphere at the equator. Above the equator, the circles get smaller. They go to a point. Below the equator, they get smaller. They go to a point. So whatever shape Dante's describing looks like that, but with every slice replaced with a sphere. It just looks like raising the dimension of this one case up. And you can show that actually works. So the space you get by stacking spheres like this on top of each other lives in 4 dimensions instead of 3. And just like this case is the surface of the 3-dimensional ball, this is the 3-dimensional surface of the 4-dimensional ball. So we call it the 3-sphere. It's the analog of the sphere we know. And that's an example that ends up looking like R3 everywhere, but is not R3. This is the first case where we go, oh, geez, it's probably going to be complicated. There's at least one thing. Once there's one, what's going to happen next? So what I would try and do is I'd say, okay, I know some stuff about surfaces. Can I make new weird examples of 3-dimensional space using my knowledge of surfaces via analogy, just like Dante? Well, actually a lot of surfaces, even though I said they're kind of easy, they're classified by genus, they're still kind of hard to work with, to picture. Like there's a lot going on. So let's start simple. We looked at the ball, the surface of a sphere. Let's look at a donut, a genus 1 surface, and say, can I make a 3-dimensional version, a 3-dimensional analogy to the donut? The way I would do that is I'd say on a donut, well, how can I make a donut? I can actually make a donut by taking a square or a rectangle, roll it into a paper towel tube, and roll the ends together, get a donut. So if I tried to do this in 3D, I couldn't start with a square. I'd have to start with a 3-dimensional square, aka a cube, and I would have to roll the sides of this 3-dimensional square together. I'm not actually going to be able to do that because there's not enough room and space for me to do it. But I can imagine what would happen. What would happen for my little ant Copernicus that lives in my square? He would walk off this side, and he'd actually appear right over here because these are the same side, right? Like they're actually glued to each other after I've rolled them up. You'd just be able to walk around in a circle. But here it would look like teleportation. Same thing over here. I could take a cube. What does it mean to roll a cube up in the dimension I can't see? To us, the little ant people that live in 3-dimensional space, it means that there's a teleportation rule. When I walk out one side of the cube, I shouldn't jump. I teleport back to the other side, and then I walk out. If I go out the top face of the cube, I appear out the bottom, because those are really bent around and glued to each other. Oh, yes. So actually, if people want to see this, I will post a link if you want to. So I made a 3D simulation of what it's like inside of that space, where there's the Earth and the Moon flying around, and you can fly around. I'll post a link somewhere, and I can try and distribute it to people. Okay, so we know the problem is legitimate. There's an actual question to be asked here. What are the 3-dimensional worlds? We didn't spend that long, and we convinced ourselves there's at least 3 of them. So there's probably a crap ton. How are we going to find them all? Well, if we look back to our 2-dimensional case, we say, what worked? The problem looked really scary. And then someone had a good idea. They said, well, actually, it's not so scary. Every two-dimensional world comes with a nice type of geometry that goes on it. And that lets me attack it with lots of math. I can attack it with analysis and group theory and geometry, and I can get a classification. Can I do that in 3D? So this is like our, our three-dimensional fever dream of math. Can we do this? It worked once, let's try it again. And the story I want to tell you for the rest of the talk is that it does work, kind of, sort of, a lot harder because it's three-dimensional. But the version that this idea that comes from the theory of surfaces works in three-dimensional space. Took a long time to figure out the details of, but in the end, it's been very successful. In particular, if you've heard of the Poincare conjecture, which is one of the millennium problems, one of those problems they put out in 2000 that $1 million bounty if you can solve them in math. Only one has been solved so far. And its solution was solved by figuring out how to do this in 3D. So you can get that as a corollary of understanding this. Now, work was finished by Perlman, so that's what we're gonna talk about the buildup. I'm not gonna tell you how to prove it. I don't even know how to prove it all the way. But I want to be able to tell you the statement of the theorem. What is the three-dimensional version of geometrizing surfaces? How does this work? And what goes wrong? So the first thing we'd need is, in 2D, we knew what types of geometry we needed. We had a sphere, we had a plane, we had a unit disk. Unit disk was hyperbolic space. And we could use those three geometries. So what is the analog in 3D? Well, if this is two-dimensional hyperbolic space, two-dimensional flat space, two-dimensional spherical space, we already saw there's a three-dimensional spherical space, thanks to Dante. We know there's a three-dimensional flat space because that's where we are. And probably not too surprising, there is a three-dimensional version of hyperbolic space. So these are some images. I got during the pandemic really into ray tracing in Riemannian manifolds. So these are some ray traced images from the inside of those geometries, versions of tilings. This actually came out of a collaborative math project. If you want to look up what's going on here, I'm not going to talk about how do you make these images, but it's a project with me, Henry Siegerman, Sabeta Matsumoto, and Remy Coulon. We got a paper up on the archive called Ray Marching Thurston Geometries, if you want to see lots of pictures like that. But that gives us three things. There's a version of all the geometries that we know from 2D. But it's actually not hard to see there's probably going to be more. In particular, once I know about a two-dimensional geometry, like the hyperbolic disk, I could stack them, like a big stack of CDs. And now I'm going to get a new thing. I'm going to get a stack of my two-dimensional geometries, and that's 3D. So that gives me that. I could also stack copies of the Euclidean plane, like a big stack of Euclidean spaces. But we already know about that one. That's Euclidean 3 space. But I could also stack spheres. This one's harder for us to picture. But you would take actual round spheres and stack them on top of each other in 4D, just like you stack circles to make a cylinder in 3D. And so altogether, that gives me two more geometries. The geometry of a sphere times a line and the geometry of the hyperbolic plane times a line. So there's at least 5 of these things we're going to have to consider. And you might hope we're done, but we're not. But it's not hopeless. There's only 3 more. And they come from studying three-dimensional Lie groups. So I'm not going to talk about these today, but the classification actually comes from understanding some stuff in algebra, which is a cool way for that to influence our study of shapes here. It might not have been what you expected, but it turns out there's 3 more. This one is called nil, this one's called SL2, and this one's called sol. I think we got a little uncreative when we started naming things. This is named because the Lie algebra associated to is nilpotent. This one's named because its Lie algebra is SL2. And this one's named because its Lie algebra is solvable. So really just reminding us of that connection. OK, so in 3D, there's 8. Not 3 geometries, but 8 of them. Here's pictures of a bunch of balls in those geometries just for fun. The top row is the constant curvature ones that we looked at first, Euclidean, hyperbolic, spherical. The next row are stacking, and the next row are the weird ones that come from three-dimensional Lie groups. So if there's going to be a version of our great theorem from dimension 2, it's going to say something like every three-dimensional world can be made out of these. That would be my first hope. And now let me see if that's what I say my first hope is in the slides. Oh no, I forgot. I should tell you what these geometries are called. Altogether, these are called the Thurston geometries after Bill Thurston, who is the visionary that led to the conjecture I'm going to describe today. Geometrization is this program of how do we extend this two-dimensional result to 3D. And not only were these geometries discovered by Bill Thurston, but the idea of how this program was going to work came from Bill's work in the 80s. So my hope is three-dimensional worlds, I want to sort them into buckets. I hope I can use these geometries to help me sort them into buckets. First test, I know a couple three-dimensional worlds. Do those three-dimensional worlds get sorted into these geometry buckets? And at first it's looking good. I can take the three-dimensional torus. Remember, that's the cube with the sides identified up. Teleportation rules out all the faces of a cube. And if we believe that what happens in surfaces should model what happens here, I said for surfaces, we associate the geometry of the surface to some sort of a tiling of space. Like I said, we had a picture of like a bathroom wall with some nice little square tiles that represented the torus somehow. Same thing works in 3D, that correspondence at least. So the existence of triply periodic patterns in three-dimensional space, like this, or like a tiling by cubes, tell us that we can use flat geometry to understand the torus. Success. We can actually also understand other scary things that are out there. So I wrote down before this example of Klein, the surface that was defined by a bunch of complex numbers in an equation. You can also make three-dimensional spaces defined similarly. So here's a collection of two equations. Plug in complex numbers to these. Write down all the solutions. You can show that the answer is a three-dimensional space. And so we should ask, hey, can I figure out, does this fit into one of my geometry buckets? And it turns out it does. This example was discovered by Poincare at the end of the 1800s. It disproved one of his ideas that he thought was going to really help us unlock things. And it actually showed us just how difficult it was going to be. But this example can be made out of spherical geometry. It can be made using a tiling of the surface of the four-dimensional ball. So 2 for 2. Two shapes we know about, generalizing two things we've done. They fit into these nice buckets. But can we always do this? No. Unfortunately, we can't. Actually, we can almost never do this. And it turns out for a reason that once you understand where the reason comes from isn't that surprising. So the problem is once you know that there's these different buckets of geometry that you could sort spaces into, I can make new three-dimensional spaces in a rather interesting way, which is luckily kind of known to people from sci-fi. I could take two worlds and I could make a wormhole between them. What do I mean mathematically by make a wormhole between them? Well, I can draw a two-dimensional example here. Here's some two-dimensional world. Here's some other two-dimensional world. And I want to connect them with a tube. In 2 dimensions, what's a tube? A tube looks like a cylinder, right? A cylinder, what's a cylinder? It's a stack of circles. So what would the 3-dimensional version of this be? I take 2 3-dimensional mystery worlds, and I want to connect them with a tube. But that tube should be a stack of spheres. And what would it look like if you lived here? I think this is probably broken, but I'm going to be optimistic. Okay. Anyway, let's go back for a second then. What would it look like if you lived here? Well, over here you would live in some nice 3-dimensional world where you're hanging out. And you would see in front of you a sphere in space. And inside of that sphere, you'd see another world. Maybe like if there was one of these in this lecture hall, there'd be a sphere right here, and inside of that sphere would be like Hawaii or something. Not just a picture of Hawaii, but literally a tube to Hawaii. You walk into that sphere, and you pop out in Hawaii. I wish we had these. But what runs into a problem for us is we know that there's at least some shapes that have different geometries to them. if this space had one type of geometry and this space had a different flavor, and I connect them with a tube, and I ask you what geometry does the whole space have, it turns out you can't put a nice thing on the whole space. What wants to happen on each of the sides, there's no way to make it agree. There is a little work there to like show why isn't there some third weird geometry that I could use, but unfortunately, you can't. And a question that might come up when you're describing this problem is, why doesn't this happen in dimension 2? Like, obviously, I drew a wormhole in dimension 2. We know how to do things in dimension 2. Like, Steve, what are you missing? And I can't explain the whole answer here, but I'm going to try and draw a quick picture to explain like the type of, there's a lot of math that goes on here. And just to give a sense of what sort of math goes on, is two-dimensional tubes actually turn out that a two-dimensional tube, like a cylinder, can be made by rolling up a sheet of paper, which is what I'm trying to draw here, like a scroll. A three-dimensional tube, a stack of spheres, can't be made by rolling up a three-dimensional space in a nice way. And what it comes down to is the cross-section of one of these tubes is a circle, and a circle can be unrolled into a nice line. Like you can think about wrapping string around like a spool. But there's no way to do that for a sphere. A sphere can't be, like if you've ever tried to wrap a present, like I tried to wrap a soccer ball for my little brother once, like you can't wrap a soccer ball the same way that you can wrap a tube. And that's what runs into kind of a problem here. So what do? Well, we admit defeat, and then we try and update our dreams. We set a more realistic goal. So my dream was sort every three-dimensional world into a nice little geometry bucket. Reality says the world of three-dimensional worlds is too complicated. I can't do that. But so far I've only found one problem. The problem is if I had a wormhole between two types of world that looked very different. So what I'm going to do is make a definition for, I'm going to talk about a good type of 3D world, a wormhole-less world. And I'm going to call that a prime three-manifold, manifold that can't be built by connecting pieces together. So this is not prime. This is two very different worlds connected by a tube. This world here is supposed to be a cartoon of something that is prime. It's not built out of a bunch of things using wormholes. And once you have that definition, you could ask, well, is every world built this way? Like I can define wormhole-less worlds, but is every world a wormhole-less world connected by wormholes? Or are there other worlds? Like is there something else? And this is a theorem. It's called the prime decomposition theorem. It was first proved by Helmut Kneser and then John Milner, finishing up a bit later, so the 20s and the 60s. And it says that this actually works. Every three-dimensional world, every three-manifold, can be built from prime three-manifolds, three-manifolds that aren't built out of complicated things with wormholes, just using wormholes. So, oh yeah, here's a cartoon of that. So the top world is some complicated world. The orange spheres are the wormholes. Think about that like if there was an orange sphere in this room, that's how I would get to Hawaii. I would jump in the orange sphere. What this theorem says is you can basically take a three-dimensional world, you can find wormholes in it, you can snip along all the wormholes, and the pieces that are left over are things that we're going to call prime. So what's our updated question? Well, my original hopes and dreams have been dashed, but I'm not going to let that get me down. I'm going to say, okay, is every prime manifold geometric? Can I sort these wormhole-less worlds into geometry buckets? That would be awesome. Or at least almost good enough, right? Like this would tell me not that I could use geometry to literally understand everything, but it would tell me that once I used geometry to understand pieces, I could then use geometry plus wormholes and understand everything. I would have Lego pieces. Each geometry would be Lego bricks, and I'd have one type of Lego connector, a tube, and I'd just be able to shove them together, and I'd win. Unfortunately, I don't win. The answer is no. Not every prime manifold is geometric. The world's too interesting for the solution to be that simple. And luckily, the solution's kind of understandable. What's the problem? Well, our original problem was wormholes. And the way that I described wormholes to start with, i.e. connect sums in three-dimensional topology, was the way you think about them in sci-fi. It's like a bubble that you can jump through to get to the other world. But why does it have to be sphere-shaped? That was just a prejudice of our imagination to start with. Why should the hole that connects me to another world be shaped like a ball? Why couldn't there be a donut-shaped wormhole? I could walk through the middle there and I would stay where I was. But if I walked through the surface of the donut, I would get to Hawaii. Like, why can't that happen? And then second, if that can happen, once you've had the idea that maybe that could happen, you can easily show it can. You can just build worlds like this. How do I do it? I take two worlds I know about. I scoop out a donut from each one, and then I glue those donuts together. I build something that has a donut-shaped wormhole. That doesn't tell me I'm sunk. That just tells me donut-shaped wormholes are a thing. What would tell me I'm sunk is if I could find a space with a donut-shaped wormhole where there wasn't a nice geometry for it. And I have an idea on how to do it. I knew it worked for sphere-shaped wormholes. I take two worlds that have different types of geometry. I try and glue them together, and it doesn't work. Maybe I should take different types of worlds and glue them together. And it turns out it's actually even easier than that here. You can take the same world and you can glue it to itself. They don't even have to be different types of geometry. They can be the same type of geometry glued along a donut wormhole, and you can still run into a problem. So again, there's a lot of really interesting math here that I tried to draw a nice cartoon image. I'll explain in a second. My sister said this is creepy when I was showing her pictures from my talk, so I apologize if you also think this is creepy. But the part of math where this comes up is three-dimensional topology of knot theory. So where we get these examples from is if you take a knot or a link in the three-dimensional sphere or in three-dimensional space, and you drill out tubes around them, what do I get here? I get a shape that has two donut holes in it. And what I could do is I could take two copies of that shape. So this is an abstract version. There's like a donut hole at the end and a donut hole at the end. And I could double it. I could just make a second copy of the world, like name it Universe 2. And when you walk through the first donut hole, when you walk through the donut, you appear in Universe 2. And if you turn around and you walk back through the donut, you appear in Universe 1. And it turns out that when this knot complement here has a certain type of geometry, it doesn't work. Namely, when it has hyperbolic geometry, when you try and make two copies of it like that, you can't put a geometry on the whole thing. It just doesn't work out. So our hope is sunk, but it's not completely sunk. I'm still optimistic. I have an idea. We had a problem with spheres, so we made some theorem. You can snip all the sphere-shaped wormholes into pieces. Now we got a problem with donuts. Let's snip all the donut-shaped wormholes. Can I do that? Can I find some collection of tori inside of my space to cut along and prove that the pieces that are left over are simple or simpler? And we can. This is called the JSJ decomposition. So this is work of William Jacob, Peter Shalin, and Klaus Johansson in the 70s. So there is a way to find inside of one of these three-dimensional spaces, one of these prime three manifolds with no sphere-shaped wormholes in it, a collection of donuts, where when you cut along these donuts, you get simpler spaces that don't have donut-shaped wormholes, more or less. It's a little more complicated to say precisely what it means, but the pieces can be understood. They fall into two categories. One of the categories is called Seifert-fibered, meaning there's a nice geometry inside of there dealing with circles. And the other category is called atoroidal, which means there's no donut-shaped wormholes. So here's our cartoon. We start with a world that has no sphere-shaped wormholes. And we look inside of it and we say, do you have donut-shaped wormholes? And we find them. And then we use this decomposition to say, once I cut along them, these pieces are all provably nicer than the first piece. They are one of these two types I mentioned. They're either Seifert-fibered or they're atoroidal. And so now I'm feeling pretty good. I'm like, maybe these are the true thing. But someone who's maybe not so deeply invested in the story might look at me from afar and be like, Steve, you've fallen down a trap. What's going to happen next? I don't like where this is going. You told me how the classification of surfaces goes. Then you tried to classify three-dimensional spaces, and you ran into a genus 0 problem. And then you tried a little harder, and you ran into a genus 1 problem. Like, did you forget what you just did? Isn't there going to be a genus 2 problem, a genus 5000 problem? Like, is this ever going to end? You want to get all of these geometric pieces. And so far, you've just been happy to say, let's keep cutting along different surfaces to try and simplify. Are you going to stop? Or are there going to be wormholes like this that we're going to have to deal with? Am I going to be able to walk into some complicated surface like this to get to Hawaii? And the wonderful conjecture, the thing that I want to be able to state for you, what we're working towards, is the geometrization conjecture of Bill Thurston, which for our purposes says, don't worry about more complicated wormholes. It's really an optimistic statement from this perspective, saying, once you've cut along the spheres and the tori, sure, there might be genus 5000 wormholes. They might exist. Again, once I've told you that you could think of them, you can make a space that has something like that. Drill out two surfaces, glue them together. But the conjecture says don't worry about that. Once you've cut along the pieces, we can sort. And this was proved in 2002 by Perlman, which is what solved the Poincare conjecture. So now, perfect, I will just state the theorem, and then we're good to go. So the geometrization theorem says every closed orientable three-manifold can be decomposed along essential spheres and tori, that is, cut along the sphere-shaped wormholes and the donut-shaped wormholes, so that every piece admits a finite volume, complete homogeneous geometric structure, fits into one of my 8 categories. And so the way I think about this theorem is three-dimensional spaces are built like Legos, out of pieces that have 8 types, and out of gluing rules that have 2 types. You can glue these pieces together along spheres and along donuts, and that's it. If you understand all those pieces and you understand the gluings, you can maybe piece it all together. So it gives us hope. And here's the cartoon of what this means. Start with your big scary space, find all the wormholes, snip, 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 and then every piece that was originally just some floppy topological object gets sorted into some nice type of geometry, different colors for different geometries here. And so these tell you what Lego pieces you need to build that original space. And so then our question in three-dimensional worlds is, what can we do with all of these Legos? And that is the perspective that really got me into this area, was saying, like, there's this awesome theorem for how to understand 3D. How can we use it? And so that's where I'll leave us.